So, good evening uh, to you. Today's topic is about introduction to spectrophotometer, right? So, when it comes to the spectrophotometry, of course, it is all about how the light travels through a given solution and the absorptivity of that solution, what amount of light it will absorb, what amount of light will get transmitted, and on the basis of that, how we can characterize the analyte in the sample. In the college, you have used colorimeter. The advanced and more applicable version of colorimeter, if it is to be talked about, it is spectrophotometer. As in colorimeter, you have a light source, then a cuvette. In between these two, you have a slit, a filter to choose, then the cuvette in which you keep the sample, and then the light is allowed to pass through that sample, which is filtered. So a select range of wavelength band that is allowed to fall on and that passes through the sample, the absorbance is noted. That is how you try to find out the concentration of analyte using the basic principle, that is Beer-Lambert's law. So the advanced version of colorimeter is spectrophotometer. And the light source, when we talk, it could be uh, the simple white light, or it could be UV light, it could be IR light source, depending upon the type of spectrophotometer that is in use or you are aiming to use, depending upon what kind of property you want to find out. So, coming to the basic thing, that is Beer-Lambert's law. So, when it comes to the molecular arrangement for any given molecule, the atoms are arranged in a specific order. We know that, right? And in a substance, in a compound, in a material, all these molecules get arranged in a specific manner. So when we are looking at a specific molecule, say KMNO4, right, potassium permanganate. So the molecule is going to have K, Mn, and oxygen, four atoms of that. They are arranged in a particular fashion. So that molecular arrangement is going to be responsible for absorption of light and also for under which in which zone, that is which wavelength it will absorb, that can be varying, or that is going to be vary if you compare the same property with some other solution, say copper sulfate. Right, the absorption of light quantity is going to depend on how much is the concentration of analyte, but the light source, from that what wavelength that sample solution will absorb will depend on the molecular nature of that analyte in the sample. So KMNO4 will absorb different wavelength, copper sulfate will absorb different wavelength. So you have to understand the principle, that is Beer-Lambert's law, on the basis of which colorimeter or its advanced version, that is spectrophotometer, works. So when we are talking about Beer-Lambert's law, uh, each wavelength of light which is passing through the spectrophotometer, the intensity of the light passing through the reference cell is measured. Now, reference cell is uh, of course required, and in colorimeter, do you remember, you have a sample that is kept in a cuvette and you take the reading, but before that you put blank and take the reading, then adjust the zero, and then you put the sample. You also keep reagent blank, right? So this is just to nullify the absorbance of light due to this medium, that is the aqueous medium. Then the color, that is, or the concentration of the reagent that is added to it, if it remains unreacted with the sample, then it should be nullified. Its absorbance is to be taken care of so that you can quantify the analyte under study. So this is a very simple schematic diagram that shows here there is a light source. Here is the sample holder, which is called cuvette. So as light passes through the sample, some of the light will get absorbed and some of the light will be transmitted. Now the light amount of light that is falling onto the sample is referred to as I0. That is I for its intensity, right? So when out of say the concentration of the analyte, if it is going to increase, the amount of light absorbed going to be more, and if it is going to increase, exponentially proportionate, right? So more the concentration, more increase value you will see, and it is proportionate also. But when the molecules are like biological molecules, it is going to be applicable. This rule is going to be applicable up to a particular limit, beyond which the complexity of the analytes will not allow this Beer-Lambert's principle to work, and same applies in simple chemical solutions like copper sulfate or KMnO4 when that solution concentration exceeds, so that no light will be passing through it, no light will get transmitted through it, all the light will get absorbed. Then you are not going to have the reading on about the transmitted light, right? So there ends the limit of the Beer-Lambert's law. At a particular concentration, the law cannot be applied to find out the concentration of the analyte in a given sample. That means if I start with the experiment that in this cuvette I have kept simple water, to that simple water I have just checked how much amount of light it is absorbing, how much light is transmitted, then I add some amount of soil into it. Then I shake the suspension, make the suspension. Or you can take a bacterial suspension also, not necessarily soil suspension. The dilute bacterial suspension, then little heavy suspension, even more heavier suspension, like that. If you go on increasing, absorbance values go on increasing. And up to a limit it will increase. After that it will plateau off. So this kind of nature is quite obvious, because the amount of light that is going to get absorbed will be maximum if the concentration is very high. So this is very general terms I am using. We have to go very specific now here onwards. So here light is there, weight is there, which is the sample holder. Light is passed through, and the amount of light will be absorbed. The amount of remaining light will be transmitted. Now, when I'm saying the intensity of the light passing through the sample cell is measured, it is measured at a particular wavelength. As I told you, in colorimeter, you use filters. 420 filter, 450 filter, 620, 540 filters, like that. But in spectrophotometer, you can choose a single wavelength. Now, the intensity of light that is passing through is given the symbol I. So, when I'm saying about the light that is falling onto the cuvette and the amount of light that is transmitted, they are not going to be of same uh, quantity wise, right? Because some amount of light will be absorbed. So if I is less than I0, then the sample has absorbed the same some light, right? Now this some light is how you are going to decide that some light, yes, that some light is going to be characteristic of that particular analyte, and when it is exposed to a particular wavelength. So I and I0 are the two entities. If I is less than I0, I is the light transmitted, I0 is the incident light, then you can say some amount of light is absorbed, right? When I say absorbance, it is indicated by symbol A, that is capital A here. So the absorbance is going to be directly proportional to the concentration of the solution which is there in the sample. And of course, it is going to be proportional to the length of the light path. So in the previous slide, if this is my cuvette size, if the cuvette size is reduced, the distance that light path has to travel through the sample will be less. If I take a bigger vessel, a bigger cuvette, right? Of course, the instrument should have that socket to keep that size of cuvette fits into it. But yes, so there are certain instruments which have the provision for cuvette having diameter 1 centimeter. Some are having some cuvettes that are having 4 centimeter diameter also can be used. But of course, only the thing is the socket which is meant for sample holders to be kept in, that needs to be different, and different what we say the spectrophotometric instruments of different brands and different application labels will give you this flexibility, whether the cuvette of 1 centimeter is to be used or cuvette of larger size is to be used, right? So when I say this, absorbance is directly proportional to concentration. That is first statement. Second is absorbance is directly proportional to the path length that light has to travel through the sample. So When I talk about Beer-Lambert's law, it can be very well simply expressed as A is proportional to C. A is the absorbance of light, C is the concentration of the analyte in a given sample. So when I say the absorbance, how to define it? It is defined via the incident intensity, that is the light which is falling onto the sample, and the light which is passing through the sample and is still remaining, which is transmitted, and that is measured. So I0 is the incident intensity and I is the transmitted intensity. So what is the relation between these two? That is nothing but the absorbance, which can be dictated in terms of a equation that A is equal to log to the base 10 I0 upon I. So log to the base 10 I0 is intensity of incident light upon intensity of transmitted light. Second expression is A is proportional to L. L is the path length. In some equations, you will find some other letter in place of L. Many a times it is B. So it is B for path length, C for concentration. That is how it goes. So it is, don't get confused with the different letter that is if it is used. So ultimately, if you combine these two equations, that is absorbance is proportional to concentration and absorbance is proportional to path length, together absorbance is controlled by two factors, concentration and path length. So A is proportional to C and L. Now, this proportionality sign I want to rule out and I want to convert it into equal. So A is equal to CL. That is not possible. There has to be some constant, proportionality constant. So here the equation is redesigned as with the proportionality sign gone, and you are having sign of equation. All right. Now this proportionality constant, which is shown by letter epsilon, sorry, symbol epsilon, is characteristic of each molecule. Its own arrangement, its own components will decide how much concentration at what path length will absorb how much of light. In short, to say, copper sulfate will have different epsilon value, and KMnO4 will have different epsilon value, right, which is characteristic of the analyte under consideration. So the formula, when I look into it, if I rearrange the value for A, how do I get is A is equal to log to the base 10 I0 upon I is equal to epsilon LC, where epsilon is the proportionality constant, which is referred to as molar absorptivity coefficient, or it is also called as molar extinction coefficient. So uh, when you talk about the absorbance, generally we take the range between 0 to 1, right? Of course it can go higher than that also, but the instrument that you have handled, say colorimeter, you have seen the maximum value for absorbance that can be noted is 1. So an absorbance of 0 of some wavelength means that no light of a particular wavelength has been absorbed. But if it is showing 0.10, 0.20, like that, 0.99 and 1.0, ultimately when it is showing 1.0, that means there is complete absorbance, and there is no transmittance of the light, right? So the intensity of the sample and the reference beam are both the same, and the ratio of I0 upon I is 1, and the log to the base 10 of 1 is 0. That time no light is absorbed, all right? So you may get some simple equation, simple numericals based on these equation, which to which we will come later on. But just now, to revise, what is Beer and Lambert's law? It is absorbance of light is directly proportional to concentration of analyte in a given solution, and also it is directly proportional to the path length of, that is the diameter of the sample holder or the cuvette that you say, and it is denoted by letter A. Absorbance is equal to log to the base 10 I0 upon I. Now, combining the two equations, you have come to the conclusion that absorbance can be calculated using the formula that epsilon LC, where epsilon is proportionality constant, that is defined as molar absorptivity or molar extinction coefficient. L is the path length and C is the concentration of analyte in a given sample. Now, when I say spectrophotometers, it is based on the same principle, that is Beer-Lambert's law, how it works. We will go to the details of Beer-Lambert's law in the next lecture to more details. Today's is just the introductory lecture on spectrophotometer. So when I say spectrophotometer, it is about uh, the wavelength that you are going to use, instead of filters, a single wavelength can be selected. Now, this is a very useful analytical instrument when it comes to chemical analysis or even biochemical analysis, for characterization of analytes, for finding out their concentration, for finding out the purity, for comparing the kind to find out or monitor the kinetics of certain biochemical reactions, to find out the structural variations in a given molecule, how these different applications would be working. I mean, how spectrophotometer must be working to navigate all these applications, that we will learn as we progress in the discussion. Now, when I say this spectrophotometer, naturally it is going to have four common components. One is source of radiation, that is light, and source of radiation is going to change with type of spectrophotometer used. For example, visible spectrophotometer, visible light. UV spectrophotometer, you will have UV light. IR spectrophotometer, you will have to use the light source which will generate IR radiations, right? So, but common is the source of radiation. Then you are going to have an optical system. So as in the colorimeter there is a filter system, here you have to have monochromators. The word itself tells you mono is to single, right? So you have to isolate the wavelength, and a single wavelength should be selected that will be falling onto your sample, and you are going to characterize that analyte based on the absorptivity principle. Now the concern is how to choose this particular wavelength. Now, just for time being, I'll tell you the components of monochromator design we will see in the next part of the discussion. So monochromators are nothing but mainly the prisms, right? Plus diffraction gratings. These are the two words which are going to be useful when you talk about monochromators. So monochromator includes prisms and diffraction gratings, so that you are going to select a particular wavelength, and that can be used to characterize your sample. So that light from the light source, only a specific wavelength of, that is, say, 267 nanometers, 271 nanometers, 280 nanometers, 110 for IR I am talking. The range is very high, up to thousands, 4000 tak jata hai, near IR, far IR, etc. So nanometers range, single wavelength you can choose. And that can be selected depending upon what is your analyte. How to select that we have done in the practical. See it in the next lecture, we will discuss upon that. Then you have to have the sample holder, in which the sample may be liquid or gaseous depending on type of spectrophotometer that you are using. You are going to hold, and a detector system, which is going to be the very crucial part in this. So FID detectors, or you are going to have various types of different types of detectors, about which we have to talk in details. But yes, the detectors and photomultipliers are there. So whatever the signal received needs to be amplified. If the concentration of analyte is low, the amount of absorbance will be very less, and the signal generated needs to be captured, so it is going to be multiplied. So what photomultiplier tubes may be the part of detection system. So how is it, how all these things components are arranged, how do they work, that we have to see in the next part of the discussions. Now, when I say a spectrophotometer, it can be of two types: either single beam, in which the light beam takes a single fixed path and measurements are taken, and without the sample present, that is what you are going to have. That is like in the colorimeter. So you initially put weight with that is filled with distilled water, check the absorbance, bring it to zero, remove it, and then you keep the sample. Right. So here you have only one path of light. But can you imagine if that cuvette having water, distilled water, which is to adjust the zero, and your sample both are kept simultaneously. So you have an arrangement which will be comparing the absorbance by distilled water against that absorbance by the sample. It will be compared, and you get the output in terms of light transmitted. So that will be a different situation, right? Where you need double beam of light. So in the double beam arrangement, the light is made to pass through two paths. one containing the sample and another containing the reference. So reference can be distilled water, reference can be a standard, reference can be reagent blank, depending upon your experimental requirements. So when we talk about spectrophotometer, there are two arrangements. One is single beam arrangement, another is double beam arrangement, right? So now here is I have taken it from the book whose reference I had given in the previous slides, so I have not repeated it here. Now let's see. When I said double beam, again there are various varieties. Double beam, there are two paths, light paths. One is passing through the sample, one is passing through the reference. But now again, when it comes to double beam type of design, there are different techniques which are used. For example, it is going to be either uh, uh, the design and the methodology that is used. It what does it mean? Not the experimental methodology. It is about the response of the detector, right? So whether it is detected by linearity method, the what is that? Let's look into it. First, we see the diagram. So you have source of light, which is passing to the monochromator. Monochromator is selecting the light beam. The light beam is divided into two parts because it is double beam. Here is the sample holder. Here is the reference holder. So light will pass through both, and whatever light is absorbed or transmitted, either possibilities you can choose whether you can keep your model instrument on absorbance mode or you can keep it on transmittance mode, whatever value you want to go for. You can ask the instrument to give the absorbance value. If you want the transmittance value to be noted, you can ask the instrument to provide the transmittance value also. There are provisions that you can directly ask for the concentration of the analyte given to the instrument, right? So the instrument will provide the concentration of the analyte directly. So you have to choose the mode, but yes, whatever the light is absorbed and transmitted will be taken cognizance of, it will be analyzed in the detector, and you will get the output, right? Now, here, if you compare this flow chart against the first one, what you see is source is there, monochromator is there, beam divider are there. One is for sample path, another is for reference, and then it goes to detector, but via optical attenuator. That is what is additional component that you are seeing in the flow diagram that we have to talk about. So when a light beam is made to follow the alternate sample and reference paths, then the detector is used to measure the intensity of each in turn, right? And the ratio gives the transmission or reflection factor at the wavelength involved. But here in the another method, if you see the optical null method, the intensity of the reference beam is reduced to equal that of the sample beam by some form of the self-control optical attenuator. So you see here additional component, that is optical attenuator, and the detector is called on only to judge for equality between the two beams. So one beam is generated by sample, another beam is generated by reference. So accuracy depends on optical attenuator. So you are going to have these possible these are the things. Why are we talking about it? Because we are talking about instrumentation. So it is about the design of instrument, principle and working of instrument, and then applications. So when it comes to principle, spectrophotometer works on Beer-Lambert's law. That's why we discussed Beer-Lambert's law. Now we are talking about the aspects of design of spectrophotometer, right? So this is single beam method or a double beam instrument. Then when it is double beam instrument, there are two possibilities. One is linearity model, and another is the one which is called as optical null method model. So in the optical null method model, what is the difference against that of the first one is that you have an attenuator which is going to judge for equality between the two beams. You are going to compare the two beams, and then the data will be provided to the detector. It will be provided the display system, and you get the digital display, or you get digital display for absorbance. It may be transmittance or it may be concentration. So in simple words to say, your spectrophotometer can be of either of the two designs. One design is single beam, another design is double beam. When I say double beam, there are two possible methods or two possible arrangements wherein you are going to have one system which is called linear method, that is without optical attenuator, and the one with the optical attenuator is called null method. So design of the instrument to show how the double beam system would work. Now this is how the optical path, right? I'm sorry. The optical path will travel. Now, may it be UV light, may it be visible light, whatever may be the type of we say the instrument, UV visible spectrophotometer, it is combined instrument. Only UV also possible that at a time you are going to use either of the two, right? So if I take example of say ultraviolet visible instrument, that is combined instrument, I'm going to have two lights, one which will work in the visible range, another which will work in the UV range. Depending upon my sample, I have to decide what light source to choose. Say for example KMNO4 or CuSO4, I want to detect the concentration of, it is my sample, then I'll go with visible spectrophotometer, and in that case the lamp or the light source will be tungsten lamp. But if I want to measure the concentration of DNA, if I want to measure the concentration of protein, for which the absorbance maxima lies in the UV range near 260 to 280, then I have to go for UV lamp. So deuterium lamp is the light source, all right? Now here uh, I have tried to share with you the light path or path diagram. So let's see the what are the parts of this diagram. You are seeing some straight lines. There are some mirrors or optical systems, right? And in addition to that, you are seeing some small letters, that is A, B, C, right? Each letter symbolizes something. What is that something that we have to understand, and that will explain you how the instrument works, right? So I have a tungsten lamp, that is the light source, or the deuterium lamp, which is the light source for UV visible. So in the UV range, you will use deuterium lamp. If you want to go for samples like which work in the visible light source, so tungsten lamp will be put on. Now this is the light source which is labeled as A, right? Then B is what? It is UV lamp. So you have either of the arrangement. So this is the optical system. So you have a mirror at an appropriate position. So the light which is coming originating from the light source will fall onto the mirror. The beam is focused by a mirror on the entrance slit, because when the light source is put on, huge amount of light it will deliver. So we don't want that much of light. We want a small defined quantity of light, so it is to be allowed. Select the proper wavelength and select the proper quantity, the amount of light that will pass through the sample. So you have to have a device that will select the amount of light that will pass through, and that is nothing but the slit. So here is the slit, right? So you are going to have this light source which is generating the light. It is falling on the mirror. So mirror is going to focus the light, and from mirror it will go to the mirror is denoted by letter C. From C it will go to D. What is D? D is the uh, the beam is focused onto the mirror, and from D, that is D is another optical system, and E is the slit. So you are going to have it passing of the light now from A to C, C to D. Both these are optical systems, and whatever light is collected by the mirror, focused by the mirror, will be passing through the slit, and the size of the light beam will be selected. Now, after that, you have a series of filters, right, which are inserted. So F indicates filter to exclude light of submultiples of the desired wavelength. The light is dispersed by diffraction gratings. That is the word I told you in the beginning. You are going to have prisms and diffraction gratings. So which is denoted by letter G. Right? And a narrow band of wavelength is selected by the exit slit K from the spectrum form. So can you see K? Yeah, it is here. So light has started originating from here. This is the bulb. It falls on the mirror system, which is the optical system of the instrument, a part of it. So C and D are those mirrors which will focus the light. The light will pass through this slit. So this is the entrance slit, which is named as E. Then you have the filters which will allow selection of a particular wavelength. Then it will fall on to G is the diffraction grating, fine tuning of the wavelength, so the select particular wavelength can be done. And then it is going to pass through the exit slit, entrance slit and exit slit. Now from through the exit slit you are selecting the particular wavelength, say 260, 261, 262 nanometers, whatever is required for the analysis of the sample that you are handling. So now it has come out of the exit slit, so you have a specific light, that is the deuterium lamp if you want to UV work. If it is tungsten lamp, you are working in the visible range, but a particular wavelength now is there, and that light again will be focused through a optical system. All right. Now you are going to adjust what wavelength you want to choose by having a meter system, by rotating the gratings of the of the instrument, and you can pick up the particular wavelength you choose. So you have chosen it, and now the beam will be divided into two parts. Why? Because you are going to have an array which is going to divide it by mirror elements at L. So you are seeing it is at, where is L? Here it is, right? So an image of the slit K are formed at R and S, the position of reference and sample cells. So because this light which is coming out of the exit slit is to be splitted into two paths, because the same quantity has to pass to sample holder and same has to pass to the reference reference holder, right? So you are talking about a double beam system. So this is how you are having double beam system. So R and S are the sample holder uh, for sample holders, which is the cuvette, right? So one is S for sample and R is for this, another is reference holder. So these two paths of light which are parallel to each other, they are generated or originated from the same source, they are splitted into two. One passes through reference, one passes through sample, and then they are going to be compared, and you get the detection, get the signal which is developed by the detector system. Now a chopper disk driven by synchronous motor, which is given the symbol M, right? Chopper disk. So what it will do, it will select the light beam, pass through only one beam will pass to the sample at a time. So chopper system is going to select the quantity of the light that will be passing. So both the beams are directed towards T. What is T? T is the silica diffuser, which is going to help the photomultiplier tube to work, and you are going to have the intensification of the signal developed. So in short to say, no need to remember all these 15, 20 lines. You can just remember this ray diagram and just remember the symbols with their meanings. What does A mean? What does B mean? What is C? What is D? Like that. So you can take the photograph of it, and then you can try to draw this simple diagram that will be useful in writing about the design and working of spectrophotometer. Right. So for today, I think this introduction is more than enough. Right. Now here, this is a simple photo that shows the arrangement of a spectrophotometer machine, and this is the display unit, because these days the automated machines are there and they are connected to the computerized systems. Softwares are there specific for specific instrument. So not only for giving the working conditions, you can select the working environment of the instrument, but the data analysis done get reflected on the screen and the format that you want. It may be a graph, table, photography, pictorial, the way you want, or certain calculations if you want. All that data can be generated and can be displayed on the computer. Right. So as you are seeing, um, this is just a schematic diagram to show how the instrument would look like. Now here onwards, we will talk in details tomorrow, but this is the last slide that I would like to share with you. So deuterium arc lamp, which is used in UV region, and the tungsten lamp, which is used in visible region. All right, generally 1,000 hours is the working life of the UV light deuterium lamp, and 10,000 hours is the working life for tungsten or halogen lamps, right? Now, what are the cuvettes? Cuvettes are of different types. They may be glass cuvettes, or they may be plastic cuvettes, or they may be quartz cuvettes. So, when you are working in the UV range, quartz cells are used, fused quartz cells are used. So, they are transparent down to 10 nanometers in the UV region. Glass cuvettes are suitable for visible range, and yes, polystyrene or methacrylate, they can be used strongly below 300 nanometers. So they are not resistant to all the solvents, but yes, they are resistant to some of the solvents, and this is like disposable material, right? So when it comes to cuvettes or sample holder, lot more to talk about, but just it is to acquaint you with the terminology which is related to spectrophotometer. So with this, the introductory session on spectrophotometer is done from my side.